All right, everybody, welcome back. As usual, I'm taking questions in the chat on YouTube and also on the forum if you're on the forum thread. So today's lesson is how's everybody doing today? Hope everyone's doing well, staying safe, staying healthy, keeping your spirits up. I know it's a difficult time. Everybody's aware of that. So hang in there and do the best you can to kind of keep people around you doing okay, keeping yourself doing okay. All right, so we're going to talk about algorithms today, and that's a really exciting point at this course. It's certainly not the last time we're going to talk about algorithms this semester. We'll talk about them really kind of continuously throughout the rest of the semester. So we spent some time in the first part of this lesson kind of really trying to be very clear about what we mean by an algorithm. This is a word that, along with I think this word has Moorish roots, right? Algebra, these words that have this al prefix, I think, go back to the Moors and their advances in many areas of mathematics. And so algorithms is a very old term. This is not a new word. But to some degree, it's really sort of started to gain a lot of relevance in the computer era. As somebody who is more on the building and creating and experimenting side of computer science as opposed to the theoretical part of computer science, I always like to remind my colleagues that do sort of more mathy stuff that if we didn't actually have physical computers to run these algorithms, it's not clear that anybody would really care. There would probably be a few people out there studying, if you had this abstract machine that could do these things, how would you get it to solve problems? But the fact that we do have these machines and the fact that they are so powerful has really given this area a lot of momentum, right? And so now that we have computers and computers are really fast and really powerful, there's become these questions of, what type of problems can we have them solve, and how can we have them solve those problems efficiently? And on some level, this is not, computing has made great strides over the past, 60 years. 70 years now, really, but this is not a solved problem. And to some degree, one of the things that you probably will see in your lifetime is computers being able to solve more and more problems, to be able to do more and more complex things. And part of that's coming about, there's really two things that are causing that. One is that computers themselves are becoming more powerful. The increases in computer processing capabilities that we've experienced over the last couple decades are just shocking. They really don't, they sort of defy our human brain capacity for understanding because we've just seen such an incredibly rapid progression in computer power. So, people like to point this out that, the smartphone that I have, in my pocket here is more powerful than the supercomputers were even maybe 20 or 30 years ago. And that's true. And it's also like no contest, right? The degree to which computing power has accelerated is just mind-boggling, right? And those of you that are taking the class now, and those of you that were, I guess, born around the turn of the millennium, are really being born into an age that is filled with more computational power than we've ever seen. And every year, of course, it keeps getting bigger and bigger. And so, at the same time, we've also been finding ways to put that power to use, and that is through the development of new algorithms. On some level, so if you think about it, these two things kind of work side by side. A better solution to a problem allows us to solve it more efficiently and use less computer power. But as computers have gotten faster, they've made it possible to solve problems in a reasonable amount of time, even using simple algorithms. And we've seen sort of these two things happening side by side. So, for example, some of the deep learning and some of the artificial intelligence, advances that we're seeing are due both to improvements in approaches to solving these problems and to improvements in the computing power. Right? There are things, some of the machine learning algorithms people came up with a long time ago, but they were just way too slow to be practical until we were able to create computers that were powerful to do them, and now we can solve these problems. So what are we talking about when we talk about an algorithm? We're talking about a solution, a way to solve a problem. Not a solution, but an approach to solving a problem that produces a result. So it's going to be a series of steps, and those steps can include all of the core computer capabilities that we've talked about up until this point. And this is another reason why this is such an exciting point in the course, because we're starting to take all these building blocks that you guys have learned and start to put them together and apply them to actually solve problems. And the way that we do that is through formulating an algorithm to solve the problem. Now, this is one thing that I want to make very, very clear, because it's really important to understand as a computer scientist. Algorithms are not code. A code is never an algorithm. A piece of code can implement an algorithm, but the algorithm exists outside of the code, right? So, one way to think about this is an algorithm is something that you could write down in English, on a piece of paper. We don't use paper in this class, but you could write in a Google Doc or something like that. So, I could write down a series of steps for solving a particular problem in English. And then I could send that to 100 different programmers. And each one of them could implement it in a different programming language, using a slightly different approach. And they could send me back the results. And then I would have 100 implementations. But I still only have one algorithm, because the algorithm is, how do I solve the problem? The implementations are, on some level, an external programming language. And in the video that you guys can watch here, I take you to the Rosetta Code site, which is a really interesting website that has collected lots and lots of different implementations of algorithms in different programming languages. So you can pick an algorithm, and you can find, sometimes like almost 1,000 different implementations in hundreds and hundreds of different programming languages. And it gives you a sense of the difference between the algorithm and all of the different implementations. So if someone gives you code, it's never an algorithm. It's an implementation of an algorithm. The other thing I can do is, if you give me code in one language, right, like Java that we're learning this semester, and that code implements an algorithm, I could implement that algorithm again in a different programming language like Python. So I could take the Java code and I could rewrite it in Python. The algorithm is the same. Both of these two pieces of code are going to solve the problem using the same approach. But, the expression is very different, right? One's in Python, one's in Java, and they're going to look different, and they're going to run differently and stuff like that. All right, so that's an important thing to get straight in our mind, right? Is this distinction between the algorithm itself, which is a series of steps to solve a problem, and the code that implements that algorithm. And throughout particularly over the next week or so, as we're starting to work with algorithms for the first time and get a sense of kind of, how things go, and, developing our own algorithms using the building blocks that we've learned so far, we're going to be very clear about this. One of the things we're going to do is we're going to always write down our algorithm in English first. And we'll actually do that using comments in, a code block, kind of, here's where the code would go. But the first thing I'm going to do is write some comments that outline my approach. And then I'll go back and step by step replace the comments with actual running code. And so this is another thing. I find this graph really fascinating. So you can actually I'll go take you there. So the Google Books project, I like this part of this because I get to sort of go on some tangents. So the Google Books project is this ongoing, I don't know how active it is today, but it was certainly active for a period of time, ongoing effort to digitize all of the information stored in all the libraries around the world. So we've talked a little bit about digital representation of information. The idea that in order to represent sound, I have to represent it as a series of samples. In order to represent text, I have to have a convention about how numbers map to characters, and then I can store text as a series of characters in an array. We'll talk more about working with text next week when we talk about strings. So up until now, one of humanity's biggest sources of knowledge and information has been libraries. And so, up until the computer era, somewhere like the Library of Congress or, the Harvard Library System, really represented in many ways, actually, hold on, you can see that, great. Really represented in many ways a store of knowledge, right? There was all sorts of knowledge and information there, a high density of information in this one building because it was full of books. Well, that's fantastic, but as we've started to use computers to process information, we want it would be useful to digitize that information. So all those books, which are on some level an analog device, right? It's not digital information. It consists of, ink on a page. We'd like to take that and convert it to a digital form, because doing that allows us to do a couple things. First of all, it's a lot easier to preserve, right? There have been, incidents in history. I should have brushed up on this before, we started talking about it. But where entire libraries in the ancient world burned down, and it just represents a huge loss of knowledge, right? You imagine, if the Library of Congress burned down. Now a lot of it has probably been digitized, and so we'd be okay. But there's probably still some stuff in there that's irreplaceable, right? That information is destroyed. And, not to make too big of a deal out of it, but that sets our entire civilization back, right? When we lose that much information, that much wisdom and learning, and that's been built up over time. So one reason to kind of try to go through and make sure that everything in the world is in some type of digital format is that then we can make copies of it very easily, store them all over the place, and maybe even if there's some sort of like meteor that hits this planet and wipes out human life, right? Or maybe if there's like 10 people left on Earth, they can sort of try to rebuild based on the information that we've been able to save. So that's one reason to do it, right? Is for preservation reasons. But the other reason to digitize information is because then you can work with it using a computer, right? And so this graph that we're looking at here, and this is just the default that comes up when you go to the books.google.com ngrams page. This is just sort of the default that you get. But the idea here, right, is that we can search for the use of particular words over time. So all this data is dated, right? So books were published at a particular time. So all the text that Google Books has scanned in and has digitized is associated with a particular point in time. And it allows us to do things like look at how usage of words has changed over time, right? So here's an example. I just happen to like the word allied, but you can see that this word, based on the Google Books data, seems like it was in, somewhat common use in the past, went through a long period of not being used, and then sort of peaked up recently, right? I'm sure that I'm sure that you guys have examples of interesting words that we could plug into this to look at the trend lines. The one that I'm showing you on the lesson today is the word algorithm. And this one, I think, is this graph is really interesting because, and this is, again, just the fact that we can produce this graph. You may think, oh, whatever, it's kind of fun, but like so much work went into this, right? There's so much technology that was required and involved to even just be able to collect this data. The Google Books project developed these really high capacity scanners that they could use so that they could very quickly go into a library and try to scan all of the books in there. They've had to deal with very old stuff that's not in great condition, make sure they can scan it safely without destroying it, right? And of course, some of the old stuff that's not in very good shape is actually the most important stuff to get digitized because it may not survive very much longer. I mean, some of these books were not meant to last for thousands of years. So here's the word algorithm, right? And you can see again, I mean, this word was around, right? And there's this little bump in the 1820s. Maybe somebody can explain what was going on around that time. Maybe this was when, Lovelace and Babbage were starting to talk about their computational machine, some of the very, very early dreams of computing that would only come to fruition a lot later. But we can see late 1960s, right? This word starts to take off and really starts to be much, much more widely used. And this really tracks along with the emergence of computers. This is also really fascinating. I mean, I was sort of looking at this yesterday. So you'll see right around 98, there's a little dip here, right? And then we see another peak ending around 2002. And then there's a sort of trough, which is interesting. I don't know. And now we're sort of starting to see this on the uptake again. So it's possible that this is sort of tracking along with maybe the first dot-com boom and bust, which, some of you were not even alive when this happened. But But anyway, I mean, this is definitely an example. Not only an example of what you can do with computers, but this. Let's see. Let's look at something like computer. That's another one that will have an interesting trend line. Yeah. Okay. So that's really interesting. 1985, right? And it's fallen since then, which again is sort of interesting, right? Maybe people don't talk about their computers in the same way. Let's see a little bit about. Let's look at the word smartphone. I mean, smartphone probably, hopefully, yeah, and hopefully it was zero back here. Yeah. Okay. So again, you can kind of you can see the emergence of certain ideas in our culture by the changes in language that accompany them, right? So, smartphone, gosh, I guess people were talking about smartphones here, but maybe just someday in the future we'll have these really powerful devices, and then now it's whack, right? I mean, you can see when they came out. All right, so that's enough fun with the Ngram viewer, but just again, I love stuff like that, right? Because that's also a great example of showing how computers are really changing other fields. There's a number of different fields in the humanities that are really starting to be revolutionized by the availability of real data, right? I mean, even something like this, you could never do this until about 10 years ago. You couldn't just say, oh, well, show me a graph of how many times a word has been used. Or if you did, you'd have to send a poor graduate student to the library for 10 years and have them go through every book and count the number of times that a word appeared on the page. I mean, you can imagine how tedious that would be. So anyway, just the ability for computers to work with new types of data is really transforming different fields. This has also been happening in art. As we've scanned in lots of different types of paintings, people are starting to do computer analysis based on that, and they're finding really interesting things. So just the ability for computers to help us analyze data is just changing the world around us all the time. All right, so we go through the Wikipedia. I won't ruin the video for you. We go through the Wikipedia definition. We talk about exactly what it is. Talk a little bit about the difference between algorithms and implementations, which again is something really important to get into your brain. And then we implement a search algorithm. This is one of those interesting days where I'm not exactly sure what to do. I don't want to ruin it for you here. I certainly do want you to go and watch the walkthroughs, because those are the most important bit of this. And we go through in each stage of this, right? So we say, okay, here's how we design the algorithm, and then we go through and we do the implementation. Throughout that, and maybe this is where I'll spend just a few minutes here before I open it up for questions. So we do talk about some new building blocks. So kind of for the rest of the semester, this is more or less how things are going to work in this class. We're going to keep solving problems using computers. And as we do that, as we go along, we're going to find a need for certain new Java language features to help us out. So the two new Java language features that we introduced in today's lesson came out of the algorithm that we implemented together. The first one is being able to determine how long an array is. So when I have an array variable, I frequently need to be able to figure out how many items are in this array. And we'll see, starting later when we start to write more general purpose pieces of code, that a lot of times when you're working with an array, you didn't create that array, so you don't have no idea how many elements are in it. And you still need to be, your algorithm still needs to be able to work properly. And the algorithms we write frequently won't have any dependence on how long the array is. So the algorithm we wrote above, where basically we're looking for a value in an array, that algorithm, the same set of steps, works identically if the array has 3 items or 30 items or 300,000 items. It's the same algorithm. Now, later in the class, we'll talk a little bit about analyzing how efficient our algorithms are and starting to talk about how many steps it's going to take for them to solve a problem. And when problems get really big, sometimes our algorithms start to take a long time, and we start to try to figure out more efficient ways of doing things. So we'll come back and we'll talk about more efficient ways of doing search, for example, which is what we did today. But when we're getting started, we're going to do things in a simple way so that we can understand it. So array variables in Java have this length property. And this is not something that I expect you to fully understand at this point. It's not something that necessarily makes a lot of sense. Why is there a dot here? That's weird. I take the name of the array, I follow it immediately by dot, and then I add the term length. That will produce the length of this array, right? So I can print it, I can assign it to a variable, I can use it as a bound in a loop. That's typically where you see it, but an array in Java knows how long it is, and this is really useful in a lot of places. All right. The other new piece of syntax is break. So break is a Java keyword that we can use to control the execution of a loop, and specifically, break, as its name implies, breaks out of a loop. So it stops executing the loop, jumps to the bottom, and then your code keeps going. So the idea is if I ever reach a break statement in a loop, that loop immediately stops. So here's an example of this in action. This is a loop that would normally execute 24 times. So if I ran this without the break statement, I would see 0 through 23 printed. But with the break statement in, I only see 0 through 9. And the reason is, as soon as I becomes 9, so I'm incrementing I each time, one at a time, starting at 0. So I have 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, get to 9. As soon as I is 9, this conditional expression becomes true. And I enter this if statement and execute the break. I jump out of the loop, keep going. So those are the two new language features that are here. Maybe what we can do, why don't we do this? If there is an algorithm that people would like to for the next 10 or 15 minutes, if there's an algorithm that you guys would like to try together, if there's a, obviously this should be something fairly simple, but would you guys like to, try implementing an algorithm together? If you have one that you'd like to see done, I can certainly do that. Elegant solution to the homework that ran a lot of conditionals. Yeah, no, not at this point. There isn't. Now, if you're clever about the homework, it should be 2 conditionals. And I think if you're clever about it, you can have it so that you should only need 2 conditional expressions. And yeah, so you might want to fiddle with it and see a little bit if you can get it. But given the tools that we have right now, no, there isn't. Now, one of the algorithms that we will implement together over the next week or so is an algorithm that goes through an entire array of values and identifies the maximum value. And that's really a better way to do it, right? That algorithm is more general. It can work with 1 value, 10 values, 100 values. And you'll also see it's more satisfying to write. So today's homework is finding the largest of 3 values. You can imagine, how would I do this with the largest of 4 values, the largest of 5 values? And as was pointed out, even the largest of 3 values is already fairly tedious. And so there's this question of, how would I do this if I needed to find the largest of a larger set of values? And the right approach is to have those values in an array and go through that array one at a time to identify the maximum value. And again, we will do that. That'll either be a homework problem or that'll be something that we go through in class. So I'm not going to do that right now. Maybe what we can do is we can look at, I feel like I'm just trying. There's so many different variants of these array problems, but I'm trying to hold on to them for homework problems because they're such good practice. So let's see here. I'm trying to think of again, if you guys have a particular simple algorithm that you'd like to see implemented, I'd be happy to do that in the time that we have remaining. Otherwise, I'm not gonna ruin this lesson too much for you. I would certainly, these are some of the longest walkthroughs we've done so far, but so these are really important for you guys to view and go through carefully. All right. Questions about algorithms or algorithms that you would like to see gone through, or really questions on material covered up till this point in the class. If there are previous lessons you'd like to see, if there's any anything that I can help you with, that I am open for suggestions about what to talk about. Because again, I feel like I've rambled and gone off on enough tangents for one day. I don't want to ruin the lesson for you, and there is pretty important content in there. I'll give you guys a few minutes to ask questions. If not, I think we'll just hang up for today and give you guys a little bit of time to go through the lesson on your own. But again, I'm more than happy to take questions. I'll just stick around for a few minutes. Are we going to do sorting algorithms? Not in the coming days. We will get there. So it's a good question. The way that these lessons are really designed, and we may enforce this more in the future, is that we do want you to watch them. We do want you to watch the walkthroughs, go through the content. Today, for example, I actually think it's pretty important to go through the walkthroughs because we're laying the foundation for stuff that's going to come in the future. What we might do in the future is actually set things up so that you can't actually work on the homework until we're satisfied that you've watched enough of the lesson content to really be ready for it. But yeah, I know it's tempting because homeworks are fun, and there's a game aspect to it, and you kind of get to write your own code and play with things, but please don't just jump to the homework problem, finish it, and then think you're done with the lesson. And for example, there is stuff that's covered in the lesson walkthroughs and in the lesson videos that will be on the quiz. I think I tried to make that very clear early on. The text of these lessons is also not designed to be self-sufficient. So you can't just read them. You shouldn't just do the homework problem. You really want to go through the lesson. So good segue into the next question. Any general strategies for doing the homework problems? Definitely make sure that you have gone through the lesson top to bottom. If you get down the homework problem, there's something that you don't quite understand. Sorry, it looks like my stream cut out. Don't know why this is. Okay. All right, sorry, it looks like there's just a pause in the stream there for a minute. So first strategy, actually go through all the lesson content, right? Once you've done that, I think today's lesson in particular sort of gives you a sense of how to approach things, right? Write down what you're trying to do first, right? That's always a really good strategy. Just if you can't write down what you're trying to accomplish, then it's very unlikely. And by write down, I don't mean in code, because obviously then you would have solved the problem. I'm talking about actually what is going on here. Why is it dropping so many frames? Hold on a sec. Something's happening here that I need to deal with. Oh, hold on. All right, well, that's better. So if you've, so sometimes if you're having a hard time figuring out how to write the code, write down what you're trying to do. So maybe actually we can do this for today's homework problem. So I'm not going to give you a solution, but maybe what we'll do is we'll come up with a strategy, right? So imagine I'm, the goal here is I'm given 3 variables, first, second, and third. And my goal is to figure out which is the largest of the 3. And one way to think about this is through a process of elimination. So when we compare things in Java, so when I have a conditional expression like this, I'm only comparing 2 values, right? Not 3. There's no way to simultaneously compare all 3 values. So if I'm only comparing 2 of them at a time, the question is, how can I produce a strategy that delivers the right result, right? And so, you might think about this. Sometimes you might use some analogies, right, from real life. So sometimes it's useful to sort of try to think of these problems like a version of a real world problem. So, I have the example of choosing, players for a basketball team, right? Which maybe you like the example, maybe you don't, but that's fine. Imagine your goal is to choose the tallest of 3 people, but imagine that you can only see 2 people at a time, right? So I have 2 people walk up to me, I look at them. Now, let's say that one of them's taller than the other. The question is, what have I learned from this? So do I know that the person who's taller is the tallest person? No, not yet, because there are other people. I've only seen 2 out of the 3 people. But what do I know, right? I know that the person who's shorter, the shorter of the 2 people, is not the tallest person. They can't be the tallest person, right? To be the tallest person, you have to be taller than everyone else. This person isn't even taller than the other person that you're comparing them to. And so that's the way that I would approach this, is sort of a process of elimination. So I start with first, second, and third. How do I eliminate one variable? So for example, if I say if first is greater than second, if that's true, what do I know about second? Well, I know that second cannot be the largest of the 3 variables. It's not possible. To be the largest, it has to be bigger than first. Now, I don't know if first is the largest either, but I do know that now at this point I'm down to 2 possible options, right? So one way to do this is inside this conditional statement. Now the only 2 variables I have to consider are first and third, right? Because second is definitely out, right? Now, if first is not bigger than second, so if second is the biggest, then I know that I don't need to consider first, right? So if I have an else statement down here, I know in this part of my code, second can't be the largest. And down here, I know that first can't be the largest, right? And so, this is one way to approach this problem. Now, when you're working with a computer, sometimes the other thing you want to do is you want to think about, how do I store information about the problem as I'm going along that might help me solve it. So in this case, you think, what is the thing that I want to store? It's which value is the largest. So let's create a variable to store the largest value. And that's gonna be a double variable because all my variables will double. So I'm gonna call this largest. And so there's this question, if I try to run this code, Java's gonna complain because I didn't initialize this variable. So the question is, what should I initialize it to? And the answer is, it sort of doesn't matter, because at this point I don't know. So I can use I can use first, I can use second, I could use third, right? I could initialize it to anything. Let's say I initialize it to first. And so I'm starting off here with the hypothesis that first is the largest, right? So here's one way to do this. So now I could say, if second is greater than first, so now I'm writing a new conditional, right? So my initial hypothesis is that first is the biggest, and I'm looking for a counterexample, right? If second is bigger than first, then first can't be the largest variable, okay? Now what could be the largest variable? Well, I've only compared 2 variables, right? And then I'm gonna put, is second the largest? So at this point, the 2 I have left to compare are second and third. So what I could do here is I could say largest is equal to second, right? So here's what's interesting, right? And I'm gonna move this comment back to here. So I can only compare 2 variables at a time, right? We've agreed on that this greater than can only take two, it has a right side and a left side, but I can't compare three variables simultaneously, so I can only compare two at a time. And so as I go through this, my goal should be at every step to reduce the number of variables that could be the largest by one. And if I do that eventually, no matter how many variables I have, eventually I can get it down to one. So the first variable that I decided to test with, the first variable, I started with this hypothesis that first was the largest. And then what I did is I basically said if second is larger than the first, then I'll save the value of second into largest. So now the question is, how many variables do I have left to consider? So if first was the largest, what would be true at this point? I would have saved it into largest, and this conditional wouldn't have been true. And so largest now contains first. If second was the largest, this conditional would have been true, and I would have entered this if statement, and I would have changed the value of largest to be second. So down here, by the time I get to line 10, the only variable that I have left to worry about is third. So largest contains either the value of first or second, depending on which was bigger. So now, on some level, I really only have two variables I need to compare, largest and third. And so, at this point, we're actually pretty close to a solution, but I won't finish the job for you. I'll let you sort of figure out how to do this. And Armand, maybe this answers your question from before about, is there a clean way to do this? This is pretty much the cleanest way that I know to do it, which is to, store the variable of largest, initialize it to first, and then with each if statement, I'm removing one variable from consideration. So at this point, I've removed second from consideration, and then all I need to do down here is determine if third is the largest variable or not. And if it is, change the value of largest to third. Yeah. So yeah, I mean, one of the things that we'll get used to as we go through the semester is this idea that the best way to solve a problem using a computer isn't sometimes the most obvious way for us as humans, right? As much as we want to write down how to solve the problem and then to try to translate it into code, sometimes sometimes our strategies have to take into account what the computer can do. So in this case, we're really kind of taking advantage of two things. First of all, I can create these variables, and this is an example of something that we might call a temporary variable. It's only being used as part of this computation. I can create variables as needed, and then I can perform these comparisons. And so by combining these two things together. Now there is a way to solve this problem without creating this temporary variable. So there's another solution to this that doesn't create a variable called largest, but that solution actually is uglier, I would say, right? It has more nested conditionals and things like that, but it's possible. So even with the problem that's this simple, there are multiple ways to solve it. And as we go through this class, initially what we're going to focus on is solving the problem, just finding some solution. If it works, awesome, right? You will get full credit. Eventually, later in the semester, we'll start to be a little bit more conscious of how our code works and looking at it and trying to figure out, okay, that may solve the problem, but is it a good solution, right? Is it elegant? Is it concise? Is it understandable? We'll start to talk about the quality of the code that we're writing, not just whether it's correct, right? In practice, both of these are very important. If you come, let's say, you're working on a problem for your boss as a software developer, and you come in and you say, okay, I've got the solution right here. I implemented what you wanted. It's this piece of gobbledygook that nobody can understand. No one is really going to care whether or not it's right or not. They're going to tell you to go back and redo it. They're going to say, okay, well, nobody can understand this. And if you can't understand something, you can't fix it. So if, you read about this in coders, right? If people have to maintain code. So just because you wrote something doesn't mean that nobody else is going to have to go back later and make modifications or fix it or try to improve it. And if the thing you wrote is so incomprehensible that nobody else can understand it, it's actually not very valuable because nobody else can help you with it. So, but yeah, good question. can you bear second and third instead of, yeah, you could. You could. So at this point, well, actually, no. So try that. Yeah, give that a try and see what happens. Because at this point, we actually don't know, the reason for that is we don't know at this point whether or not largest contains the value of first or the value of second. It could contain either, right? Here's another way to think about this from the analogy we were using before. So imagine you have a whole line of players and you're trying to figure out who's the tallest. So you create a temporary spot over on the next to you. Well, actually, maybe next to you, right? You just have, so you bring up people two at a time. You bring up the first two people and you say to the largest one, the tallest one, stand next to me. And then you bring up the next person and you compare that person with the person next to you. If they're taller, you say, sorry, you're not the tallest. You let the person next to you go and you move them next to you. So now they're the tallest that you've seen so far, and you keep going. So that position next to you, that temporary spot where you're having the tallest person stand while you kind of work through all the candidates, is very much like our largest variable here. But at each step in the process, we compare the new player or the new potential teammate with the person who's standing next to me. That's the person that so far I've determined to be the tallest. This is a particular pattern of writing code that we will see later on. And this is particularly something that we're going to use in a loop. So you can imagine taking the same approach and applying it to a loop that goes through lots of different values in an array. And in fact, that's a problem that we'll do together over the next week or so. We'll either on a homework or as part of a lesson, we'll do the maximum over an array, and which is pretty much the problem that we're describing. We're just doing a smaller version of it that doesn't use an array. There's a question about coders. Yeah, coders chapters 1 and 2. And that'll be posted on the course calendar point when I get around to it, probably today. I've been working a little bit on updating the calendar today, so we'll get the topics for the quiz and the coders chapters. But yeah, coders chapters 1 and 2. I mean, these are easy reads. I hope you guys are enjoying the book. The goal of having the quiz questions is to get you to read the book. But I think it's a really enjoyable read. So, all right. I think unless there's any last minute questions, I think we are good. Thanks for joining me, guys, and I will good luck on today's lesson and the homework, and I'll be back tomorrow.